Welcome back to The Explainer. Today, we're tackling an absolute monster of a challenge in enterprise system design, escaping the dreaded spaghetti code. Seriously, if you've ever worked with enterprise systems, you know exactly what I'm talking about. We're going to look at how to actually fix these fragile architectures and build integrations that are robust, scalable, and secure. We're basically taking systems that are totally tangled up and prone to cascading failures and transforming them into highly coordinated, efficient networks. Let's get right into it.
Okay, let's dive into our roadmap for today. First, we'll talk about escaping that spaghetti code. Then, the core principles of good integration. After that, we'll unpack the integration pattern toolkit. And finally, how to handle inevitable system failures. All right, part 1. Escaping the spaghetti code and the true cost of tightly coupled systems. Have you ever actually tried untangling a massive bowl of spaghetti code? You change one seemingly harmless line in an inventory module, and suddenly, boom, the entire payment gateway crashes. It's the absolute nightmare of tightly coupled systems. It completely kills your business agility, piles on massive technical debt, and frankly, it's the exact reason you're getting those 3 a.m. pager alerts. When systems don't have clear boundaries, a single failure just cascades through your entire network. Now, what's really interesting here is looking at enterprise integration like a massive international airport. You've got passenger apps, baggage routing, flight ops, and they literally all have to communicate flawlessly. In our digital airport, think of the APIs as the terminal gates and the data messages as the luggage moving between them. If the baggage system connects directly to the fueling system without any standardized routing, you've got total chaos. We absolutely need standardized, structured ways for these distinct systems to pass information safely. Moving on to part 2, principles of good integration. This is essentially the architect's blueprint. So, the crucial point here is understanding the balance between two major cornerstones, loose coupling and high cohesion. Loose coupling means systems function independently with minimal dependencies. System A really shouldn't need to know the internal wiring of System B. We achieve this by using intermediaries, like message queues. On the flip side, high cohesion means components focus on a single, well-defined business purpose. It's the single responsibility principle, but for integration. When you combine these two, you get systems that can evolve totally independently without breaking each other. But those two don't act alone. They're supported by a whole list of essential design principles. Standardization ensures we're all using common protocols, like JSON or REST. Resilience means designing for graceful failure, because things will fail. Scalability lets us handle growth, often through asynchronous communication, so a sender doesn't have to just sit there waiting on a busy receiver. Extensibility future-proofs the whole setup, while monitorability and security keep everything visible and locked down. Going back to our airport, these principles ensure we handle peak holiday traffic safely without losing anyone's luggage. Section 3, the Integration Pattern Toolkit. Think of this as your enterprise workbench. The first tool in our kit is the content-based router. Think back to that automated baggage sorter. It reads a tag on a suitcase and instantly routes it to either the domestic or international belt. Well, a content-based router does exactly this, but for data. It examines the content of a message, maybe a customer order, and routes it based on predefined rules. Destination is the US, boom, US shipping service. Europe, EU shipping service. Simple and effective. Next up, the message translator. In the real enterprise world, systems almost never speak the exact same dialect. A CRM system might use a customer ID, but your old ERP system is stubbornly expecting an account number. The message translator steps in as the required middleman, transforming data from a source format into a totally different target format, like quickly converting old XML into lightweight JSON so the target system actually knows what's going on. Then we have the splitter. Let's say your system receives a massive batch file with 100 different customer orders all at once. You just can't process that as one giant block efficiently. The splitter takes that single massive message and breaks it down into 100 smaller independent order messages. This lets a downstream fulfillment service process every single order individually, which incredibly speeds up your workflow. Now, the exact counterpart to the splitter is the aggregator. Sometimes you have to wait for multiple pieces of a puzzle before you can move forward. If you split an order to check inventory and process payment at the exact same time, the aggregator collects these related messages over a period of time. It waits for both the payment confirmation and the inventory reservation, and only when it has both does it combine them into a single consolidated order-fulfilled message. And this brilliantly illustrates another problem. Sometimes the issue isn't the data format at all, it's the actual communication protocol. Enter the channel adapter.
You might have some legacy system that only drops files onto an old FTP server, but your modern cloud app strictly expects a REST API. The channel adapter bridges that gap, converting the communication protocol so systems speaking entirely different technical languages can suddenly collaborate. Finally, tying the whole shebang together is the message bus, or message broker. Instead of drawing a direct point-to-point line between every single application, which creates that nightmare tangled web we talked about earlier, all systems connect to this central intermediary. It's literally the central nervous system of your architecture, usually using a publish and subscribe model. An app can publish a new user-created event, and any other system that cares about that can just subscribe to it. Which brings us to our final section, Part 4, handling inevitable system failures and building that safety net. Let's move to and see how this builds our integration failure toolkit. Because in distributed systems, failure is a 100% guarantee. If you hit a transient error like a quick network glitch, you use a retry mechanism. But what if the target service is totally down? That's where a circuit breaker is an absolute lifesaver. It temporarily stops sending requests to a struggling service so it doesn't get totally overwhelmed and actually has time to recover. And for poison messages, stuff that just won't process no matter what, they get routed to a dead letter queue for manual investigation so they don't clog up the rest of the system. But to manage all this, you need a traceable architecture. Without proper logging, fixing an error in a distributed system is quite literally flying blind. Step 1. Use contextual logging with correlation IDs. This slaps a unique tracking ticket on a transaction so you can follow it as it hops across 10 different systems. Step 2. Format with structured logging, like JSON, so machines can easily read it. And Step 3. Route it all to centralized systems. This structured data is absolutely crucial for automated troubleshooting and keeping your real-time dashboards running. So what does this all mean? We've untangled the spaghetti code, we routed our data with some great integration patterns, and we built our safety net. But I want to leave you with a final thought to really chew on. If we can decouple our existing systems so effectively using these patterns, what happens when we start designing every single business capability as an independent, reusable service from the ground up? That question right there is the gateway to understanding service-oriented architectures. Think about it and keep exploring.